Very good. Okay. All right. Good to see you all again. Now, so today will be my last lesson with you on kinematics and dynamics. Next week, another professor will take over for 2 or 3 lessons. Okay. And after that, another professor will take over, and so on and so forth. All right. So today I will finish off my lecture materials. Before I start, I would like to remind you that there'll be a midterm quiz for my materials and for the next professor's materials as well for your midterm. All right. Next, you see that my lecture materials, if you go to LMS, there is a 2B materials. 2B is for your self-reading. It's not meant for me to cover it during the lesson. It's for your self-reading. It's basically a lot of words there, about 10 slides. It's a guideline. These are guideline or steps to guide you how to apply Newton's laws of motion. Okay, series of steps to guide you. So it's for your own reading, because because by today's lesson I would have finished covering Newton's laws of motion already. Okay, so to be in your RMS is for your self-reading, for your own record and self-study. Okay, so I will not be covering 2B. All right. So after today's lesson, if you have questions, technical questions on kinematics and dynamics, you are welcome to email me on my email address. Okay, my email address is shown, I think, on my first set of slides. If not, I can give it to you in a moment. Okay. Okay. Let me just. So you can ask me. Even my lectures are over. Okay. Let me just key in. Okay. So it's wait. Okay, let me just make it larger. So that's my email address. Right. You need to contact me on kinematics and dynamics. After my last lesson, you are most welcome to do so. Okay, all right. Yeah, let me see. There are 135 of you. Very good. Okay, so I finished lecture materials 1A already, and so I cover velocity, acceleration, average velocity, average acceleration, instantaneous velocity, instantaneous acceleration. Also look at particles falling from the vertical direction subject to a constant acceleration called G. G is gravitational acceleration, and is equal to 9.81 meter per second square. Okay, so maybe I'll just ask some questions to refresh your memory. Okay, give me a moment. My visualizer is on my left, so I have to turn to the left side. Okay, you can see. You might bring nearer. Okay, so some questions to see whether you understand my lessons last week or not. Okay, so for example, like average velocity, this is a delta t. So your V average is delta S over delta t. Okay, then your V instantaneous is dx dt or ds dt. So these two are equal, only in this case they are not equal, because instantaneous velocity, as you know, the point must be 1 point only, instantaneous. Okay, so in this case, because it's a curve, the average velocity can never be equal to the instantaneous velocity. Only equal the case of when the velocity is constant. Okay, it's constant, straight line. Then the instantaneous velocity, so the whatever it is, because the average velocity will always be your slope. So average velocity any time t. Okay, your delta s or delta x or delta t, and your instantaneous velocity will also be the gradient also, or any point. Instantaneous velocity at any point will still also be the same at any point. Okay, same delta Same, because your ds dt, right? The slope, the instantaneous velocity given by the slope is equal to the average velocity between any 2 points. Okay, so when the velocity is constant, like in this case here. Okay, is that clear? Oops. Second camera. Give me a moment. Okay. All right, back again. All right, next. Okay, if you have velocity versus time plot, two vehicles origin, car one starts with acceleration because velocity increases with time and it tapers off. Okay, all right, okay. And then starts with here, same, at time t equals 0, and it goes like that. Okay, now question is, at time t equal to t, at time t equal to t, okay, this car 1, car 2, at t, at time, t equal to t. That means from here all the way, starting from t equal to 0, the car starts. Accelerate, car 1. Second car starts at same time, car 2. So after time, certain time has passed, that's equal to t seconds. Okay. At time t equal to t, which car has traveled further? At time t equal to t, which car has traveled further? They start at the same time. Okay. But they have different acceleration and different, the velocity varies with time. So at time t equal to t, when they reach here, when they reach t equal to t, which car has traveled further? So, how? Okay, Nori says cover, the one that covers more area under the graph. Okay, very good. Okay, so you see that the displacement is given by area under the curve. Okay, displacement is given by area under the curve. This is the displacement of car 1. Car 1. This is the displacement of car 2. So you can see that car 1 has greater displacement than car 2. So which is car 1. Okay, it's area under the curve for velocity versus time plot. Okay, all right. Let's call it question 2. Okay, let's just ask a few questions. Not much time. So, okay, again, this displacement. I put x here, displacement versus time. Okay, so I have one like that, and it goes like that. Okay, all right. Okay, question is, this is a car traveling. Okay, car traveling, and so you have, let's say, put a points, get various points. Call this this O. Okay, okay, P Q R. Okay, O P Q R maybe S S. Okay. Now question is, at which moment, at which point, is the speed of the car smallest? At which point is car speed or velocity? I put speed, car speed, the smallest. Answer. Okay, you have some students put Q, most put Q, one or two put S. Okay, one or two put S. Okay, now the speed is given by the, in this case, the slope of the graph. Okay, the speed or the velocity is given by the slope of the graph. So at this point here, you see, you look at the instantaneous, you get the instantaneous velocity anyway. Okay, here the instantaneous velocity is a tangent to the point on the curve. Okay, and the slope of the tangent give you the instantaneous velocity. Now here, the slope is 0. So this will give you the smallest speed. Okay, slope is 0, so it's Q. Answer is Q. Slope is 0. Okay, slope is 0, so it gives you the smallest speed. Okay, then after that, it starts to change. All right. So in other words, at this point here, instantaneous velocity is actually 0. Okay, so instant at that instant only 0. Doesn't mean it stop here. It's just what is happening is changing the direction. Okay, it's changing direction. This is positive velocity. This negative velocity. Negative velocity means what? The car has reverse direction. Okay, negative velocity. This is negative instantaneous velocity. Means what? The car has reverse. direction. Okay, so just note, negative velocity, whether it's instantaneous velocity or average velocity, doesn't matter, means car going in opposite direction. Okay, here it's going along the x direction. Here it changed direction. It moved towards the negative x direction as time increases. So negative velocity means car going in opposite x direction. Okay, put this here. Right. And okay, I think we will just stop here for a moment. We must go on with the lecture. Okay, we go on the lecture. All right. Okay, let's go back to the slides and start our lesson for today's lesson. Okay. All right. Motion in 2 dimensions. So today we will, all right, this learning outcome using vectors to represent position velocity, solving problems involving projectiles. Okay, because projectile go along a curved path. It's called a parabolic path or curve. Okay, that's what a projectile does. Okay, and relate the velocities of a moving body as seen from 2 different frames. So it's just a couple of slides only, not very much. So we'll cover this. Okay, cover this. So we know what is scalar already, what is vector. So scalar means has magnitude but no direction. A quantity has magnitude but no direction. Okay, so scalars like speed has magnitude. Okay, 20 miles per hour is magnitude. Mass, 10 kilogram, 1 kilogram is magnitude but no direction. So it's volume, 20 meter cube, as it is a scalar. Time also, 20 seconds, 5 hours is magnitude but no direction. Whereas velocity has magnitude and direction. So if I ask a question on velocity, you must give the answer with magnitude and direction. Okay, 20 meter per second along the positive x-axis. Okay, don't just 20 meter per second full stop. Then you lose a little bit of marks for not mentioning or calculating the direction. So when you're calculating a vector quantity, you must find the answer in the form of a magnitude and direction. Same for weight. Weight, because G is downward, okay, the acceleration is downward. So weight has magnitude and direction. Weight is a force. It's a downward force. So its direction is of course downwards lah. Same for frictional force. Friction force. Okay, has got magnitude and direction. It's a force. So all forces are vectors. They have magnitude and direction. So, okay, all right. So it's a torque. Torque also has magnitude and direction. Okay, so let me just quickly mention torque. Give me a moment. Use the visualizer. Okay, torque. For those of you who have no idea what torque is, okay, torque. Very quickly cover what is torque. So if you have a nut here, hexagonal nut, this is called hexagonal nut, 6-sided. Okay, so use a spanner. To loosen. Okay, to loosen. Normally spanner has got, okay, just one side also can. All right, a spanner to loosen the nut. So to loosen, you turn counterclockwise. Loosen. To loosen nut. Okay, so you apply a force. So basically you apply you apply a force. So let's say you apply a force here at this point, F. Okay, and this is the center, and this is your distance. Okay, there's a x. Okay, you apply a force here at point A. Okay, so in this case here, if you were to draw, this is a schematic diagram. If you draw a technical diagram, this will be the nut. Okay, there is your nut. The nut here, this is point A. This is the spanner up to here. This is point A. You apply a force F. Okay, this is your distance X. Okay, right? So we say torque about point N, center of the nut, is equal to TA. Okay, torque T about point N, center of the nut, is equals to F times X. Okay, and it's in Newton meter. Okay, X is in Newton, this is in X is in meter, F is in Newton. So Newton meter. Okay, torque is force times distance perpendicular to line of action of the force. So torque is force times distance perpendicular to line of action of applied force. Okay.
Torque.
Yep. Somebody asked a
What's the
question.
difference between moment and torque?
Okay. Moment and torque is a good question. So basically, when we talk about moments, we are talking about complication, a system of forces acting on a beam or whatever. So you take moments. You take moment. So torque is basically a simplest form of moment analysis. Simplest form of moment analysis. So you just have one force, okay, and it acts on a object or whatever. Okay, so you get a torque. So torque is basically one force. Sometimes you have two forces acting together, and they act about a point, direct application. Whereas for moment, moment then is quite different in a sense that if you have a beam, okay, and you got an object, you put a object one, so you got F1, and then one F2, then you have another one pushing it up, F3, and so on and so forth. So you can take moments about A. Then we say we take moments because it's more complicated system. And sometimes this can be like cantilever facing upward at the angle of theta, you see. Then you're applying F1, F2, F3, then it's get more complicated. So in the analysis like this, you apply moments. First for torque is basically a simple force acting at a point on a structure. It could be another, it could have another, maybe you could have another spanner on top of this nut. If this nut is quite thick, so you can have another spanner. So both will apply a torque to the nut, and a spanner here will also apply another torque to the nut. So if you like, a torque is basically a very simple form of a moment system. Okay, a very simple form of moment system. All right.
Okay, thank you.
Okay. All right. So that is torque. All right. Let's go back to your slides. Okay. Right. Next one. Okay. Next is the concept of velocity. Okay. So if a car is increasing velocity without changing direction, okay, if a car increasing its velocity without changing direction, so you draw a vector to represent the velocity. You get V initial there in this direction, in the X direction. Okay. Now it increases speed, without changing direction. So direction is always towards the positive X direction. Then when it increases speed, its final speed is V final, so much more than VI. Okay, so you draw an arrow that corresponds to the magnitude of V final. It's longer arrow compared to V initial, because the final velocity is greater than the initial velocity. So what is the change in the velocity between final and initial? Is delta V. The length of the big arrow minus the length of the smaller arrow. Okay, the arrow represents the vector. It has magnitude VF in the positive X direction, or VI in the positive X direction. So is delta V, the change in velocity, is given by the difference in the length of these two vectors, VI and VF, and is in the positive X direction. You see that? Now, what if you have a case of decreasing the speed? At first you start with a high velocity, VI, long arrow. Then your final velocity is small because you decrease your velocity, VF. So the difference in velocity would be VI, would be VF minus VI. Okay, the change is V final minus V initial. So V final is shorter arrow minus longer arrow, you get you get a negative lah. Shorter arrow means magnitude smaller. Smaller magnitude minus a larger initial magnitude of the velocity, you get a negative change in the velocity. Vf minus Vi will give you delta V, and delta V will be negative. It's a vector. Negative vector means it reverses, as I mentioned just a moment ago. So the negative change of velocity is negative value, the change velocity negative value, so it reverse direction. And it's the difference between the final and the initial velocity. So remember, negative velocity means it reverse, become opposite direction. Okay. All right. So that's decreasing. Now, what if a car goes along with a initial velocity of Vi, okay, and then it turns while keeping the speed constant? It goes along velocity Vi, and then it turns. And it turns in which direction? In the direction of Vf. So what is the change in velocity? Now, Vf is equal to Vi, because here it is constant. It never changes velocity. It only changes the direction only. So Vi equal to Vf. So in vector form, the change in velocity is what? Vf minus Vi. It's not zero, it's actually delta V. Okay, so the car starts, okay, go this way, and then it changes velocity. It changes direction. So it goes there, and okay, so velocity Vi, velocity Vf. So what is the change in the velocity? It's the same, Vi, Vf, same magnitude, except direction change. So change in velocity is given as delta V and is in the direction of the red arrow. Okay, it's in the direction of the red arrow. So this is schematic, as what you see. Remember, I always mention schematic is what you see, schematic diagram. Whereas this is a vector diagram. On the right here is a vector diagram. So in your analysis, mathematical analysis, you must always use a vector diagram to work on. Don't use the schematic diagram to work on. You will get wrong answers. We are always, schematic is for you to see, to visualize the problem. To solve the problem, you must convert the schematic into a vector diagram. Then you can go and solve. Okay? All right. So this is a case of maintaining the constant speed but change in direction. And that will be a delta V. Now, what if you don't keep the speed constant? Now you increase the speed while change the direction. So initially you start with velocity Vi. Then you change direction and increase the speed. Okay? Previously, you keep the speed constant. Now you increase the speed, but change the direction. So your delta V will still be Vf minus Vi. Right? So it's therefore in the direction of the red arrow. You see that? Vector analysis. So you see that changing the direction or changing the speed will change your vector diagram. And here, the main message here is you must always draw the vector diagram in order to solve the problem. Okay, the schematic diagram is for you to visualize the problem only. You must always draw the vector diagram to solve. Okay, all right. Okay, next we go on to projectile. The topic of projectile. Okay, these are the basics that we are covering. So projectile, first, a projectile is any object or any body or object with an initial velocity. So a projectile is any body or object with an initial velocity. So it starts with an initial velocity, okay, at a certain angle. So it follows a path. And the path, as I mentioned earlier, is a parabolic path, curve, as you see here. Sometimes it's called trajectory, parabolic path or parabolic trajectory. Okay, there, right? And its motion is entirely determined entirely by gravitational acceleration and air resistance, because the projectile is being thrown into the air, into the sky. So it must move the initial velocity and along a plane, like on your screen. Your screen is a plane, okay? So along the XY plane, X and Y plane, okay? And in the parabolic path. And its motion is entirely determined by gravitational acceleration and air resistance. However, because air resistance is minimum, so we can neglect air resistance and even curvature of the Earth. So we assume that OX is a straight line. OX, your OX is a straight line, okay? It's not a curve. Huh? So OX is a straight line, okay? We neglect air resistance and the curvature of the Earth. So that OX is a straight line. Because the projectile, this curve can be a very, very, very big curve, you know. Can be, OX can be 1 mile, 2 mile long. It's a military cannon, firing a cannonball all the way. Then OX can be 1, 2 miles away, you know. And we know the Earth is round. So we may say, hey, OX should be a curve. How come a straight line? But it's a very gentle curve. So we take it as a straight line. Okay? All right. All right. So we don't have to worry much about air resistance. It's the gravitational acceleration G that we need to consider. See, and motion is confined to the vertical plane, X, Y plane. Okay? It's a plane. Just a sheet of paper, that's a plane. Okay? Your computer screen is a plane. Okay? So it goes to initial velocity, see V naught there, or VO, initial velocity. Note that acceleration A in the X direction, okay, acceleration. So in other words, this V naught, initial velocity, has a component, as you know, is called V naught X. V naught in the X direction. It also has a component in the vertical Y direction. The Y direction is called V naught Y. Okay, so we know that V naught X, if this angle is theta, then V naught X is what? Is V naught cosine theta. And V naught Y is V naught sine theta. Okay, I don't use theta because I think the rest of the slide use alpha naught. So I change theta to alpha naught better. Okay, your slides use alpha naught. So I change to alpha naught. Okay, alpha naught. Naught stands for original. Original. Okay, change to alpha naught instead of theta. So V naught X is equals to V naught cosine alpha naught. Naught means the origin. V naught Y, vertical component, is V naught sine alpha naught. Okay, and the acceleration is in the, because it's shooting at an angle up. So acceleration in the positive Y direction. I see that acceleration in the positive Y direction is minus G, not G, but minus G. Okay, because your AY, you see, is accelerating upwards. Your AY acceleration in the Y direction is upward, but G is the but for as far as this particle is concerned, okay, it's subjected to gravitational acceleration G, which is downward. So the acceleration A in the Y direction is equals to minus G, okay, as shown below there. And G is 9.81, okay, equal to 9.81 meter per second squared. Okay, now notice here the acceleration of the particle in the X direction is 0. What does that mean? What does that mean? 0 acceleration means what? What happened to the velocity in the X direction? Acceleration. Okay, so AY has a component in the X direction. But because AY is vertical, so its component in the X direction must be 0. Okay, AY cosine 90 degrees. AY cosine 90 degrees. Cosine 90 degrees is 0. So AY cosine 90 degrees is equals to AX, acceleration in the X direction. So AY cosine 90 degrees is 0 is equals to AX. Therefore, AX equals 0. So acceleration in the X direction is 0. What does that mean? It means the component of the acceleration AX, the acceleration in the X direction AX is 0. That means the component of the velocity of this particle as it so-called moves along this trajectory. At any time, the component of this particle, this object, its velocity in the X direction is the same as the v naught x. Okay, so if I have particle now is here, okay, in the second position, what is component of velocity here in the x direction? Same, v naught x, same. It equals v naught cosine alpha naught. Okay, it's the same. But your v, this one vy is not the same as v naught y. No, because subjected to the vertical acceleration. Okay, so vy is a new value, but your v naught x will always be the same, no change. So here also still v naught x. Okay, no change. So in other words, the component of the velocity of the particle at any point along the trajectory remains unchanged. It's the same as the initial x component of the velocity, v naught x, which is v naught cosine x naught lah. Is that clear? Okay, yeah, clear. Let's move on. There you are. Okay, I mentioned this already. This component of the acceleration in the x direction. This component of the acceleration in the y direction. Okay, so here ax equals 0 means constant component of the x direction velocity is constant. Okay, same as equal to v naught x. So the red ball is dropped at the same time as the yellow ball is fired horizontally. Will they land on the ground at the same time? Will the red ball and the yellow ball land on the ground at the same time? What do you think? Yes or no? Yeah, okay. Ifran, good. Nori, good. Yes. And at the same time. All right. So there you are. I just mentioned this. Oops. Okay. Mentioned this. So it's V naught Y. This is V naught X. Your Vx. Yeah, this is your V naught X. This is your V naught Y. This is your initial starting velocity. Okay. All right. So now, all this is saying that we start with time t equals 0 lah. So at time t equals 0, your particle is at x naught, y naught. Okay. Now, so if you apply principles of motion along a straight line, we can apply EOM, equations of motion, as we learned earlier. Why? For projectile, why we can apply equations of motion? Remember the two conditions I mentioned to you all. To apply equations of motion, two conditions must be satisfied. What are they? To apply equations of motion to your solution, what two conditions must be satisfied? What are they? What are these two conditions? Cannot remember already. First, must be what? Motion must be along a straight line. Okay? Motion must be along a straight line. The straight line can be horizontal, can be vertical, can be at a certain angle, incline. Doesn't matter, as long as it's a straight line. Okay? And must have what? Constant something. Oh. Not constant. Zero acceleration. Zero acceleration means the velocity is constant. Okay, constant velocity, so zero acceleration. So in this case, when you say, but it's a projectile, no? It's a projectile. I thought you say the vertical acceleration is constant and not zero. But you look at this equation. We're applying the equation of motion along the x-axis. X-axis, see that? Along the x-axis. So x-axis is a straight line. And x-axis, along the x-axis, the component of the acceleration in the x-axis is 0. So it satisfies our two conditions to apply the equations of motion. Okay? So this I already mentioned to you. This is V naught x, which is initial component of the velocity. Okay? At the origin. So we can apply equations of motion. Then you can get your first equation of motion. Okay, you can apply along the y direction. Oh, constant acceleration. Not zero acceleration, but constant acceleration. Okay, but for here along the x-axis and along the y-axis, let me just correct myself. Along the x-axis, this applies. Distance or displacement is equal to velocity times time. Okay. Now, what is this x here? This x here means it need not necessarily start at origin. It need not start at origin. So in other words, it need not start at origin. So in other words, origin can actually be anywhere along here. This can be your origin. So this is your starting point, if you like. You can, let's say, this is my starting point, A. Okay. So this is your initial, this is your x naught. That means you start at x naught away from the origin. So you must add your x naught. Okay. Now, if you start at the origin here, exactly here at the origin, you call this origin, then your x naught is 0. Because you can fire projectile anywhere from the origin. You can fire from here, or in this case, you fire from here. So your starting point is x naught from the origin. Okay, so you must put an x naught there. So what's the distance covered? The horizontal distance. See, x is your horizontal distance. This is your x covered. It's simply the velocity times time taken to cover that distance, because the velocity component in the x direction is constant. So anywhere is v naught x times t, whatever the value of t is. Okay, constant velocity because acceleration is 0. Okay, so let me correct myself. The EOM must be straight line and what? Constant acceleration. Yeah, constant acceleration. Okay, so constant acceleration, now we apply to the vertical direction. See the y here? Velocity in the y direction is v naught y minus gt. So in other words, your velocity here. So remember, this component here is always v naught x, no change. But this vy will change because subject to gravitational acceleration. So what is vy? Vy is given as v naught y minus gt. This is applying first law. Remember your first law? Final velocity is equal to final velocity because initial velocity plus is equals to v naught y plus ay times t. Okay? And what is ay? Ay is minus g. So that's from your first equation of motion. Okay? So the vertical component of velocity of the projectile when it is here is given by this equation here, equation of motion number 1. And bear in mind that it's plus, Vy is v naught y plus ayt, vertical acceleration. Vertical acceleration ay is equals to minus g. Okay? Then next one, apply from the second EON number 2. So again, you have y is equals to y naught plus v naught yt minus half gt squared. It's same, you see. This is equal to y naught. Before that is y naught plus v naught y plus half ay times t squared. Okay, applying your second equation of motion. So again, you see your y naught is the same concept as your x naught. That means your projectile can be fired from here, came here. Okay, not necessarily at y equals 0. It can be fired from a certain point, y naught. All right. So if your projectile is fired really from origin here, that means your y naught equals 0. Okay. All right. So this applying your second equation of motion. Okay, there, second equation. Then you apply your third equation of motion for this velocity in the y direction. So v square is equals v naught y square minus 2g y minus y naught. So this is from your third EOM. It started off v square is equals to v naught y square plus 2ay in the vertical direction times your displacement. Displacement is okay, and ay is minus g. All right. So you have your first, second, and third EOM all apply there. To get these 3 formulas, if you like, to get these 3 formulas. Is that clear? So do not worry about x naught and y naught. X naught and y naught will be equal to 0 if the projectile is fired exactly from the origin of x and y axis. Okay? But if it's not fired from the origin of x and y axis, but further away along the x axis, then you must plus a x naught. And if it's fired a little away from the y direction, away from the original axis, original point, then you must put your y naught lah. That's all. So x naught and y naught is the same concept. It means away, fire away from the origin in the x and y direction. Okay, right. So you see, this, right? Now look at this, the symbols very carefully. This is your y-axis. This is your x-axis. This is your origin. Now in this case, it's fired from origin. Fired from origin. So your x naught and y naught are 0. Okay, your x naught and y naught are 0. It's fired from origin. So your v naught x is there. So notice that this v naught x, velocity component in the x direction. Okay, now, so your v1x will be equal to, v1x will be equal to your, this will remain unchanged, to your v naught x, no change. Okay. And so on and so forth. Okay. But your v naught y, v1 y, they will be different because they are subjected to gravitational acceleration. So you must use your equations of motion to find your answer. Okay, right. So if v1y is different and v1x is same as v0x, then your v1 will change out because that is the resultant of your v1y and your v1x. That's the resultant. So v1 will change. When it reaches the top of the trajectory, okay, it will have 0 vertical velocity. 0 vertical velocity. So your vy equals 0. Okay, so the x component, of velocity is still got a certain value. But remember, your acceleration is always in the vertical, always vertical direction. Always vertical direction. So in this case here, the component of the velocity in the x direction and the acceleration in the y direction will be perpendicular to each other. Okay, they are perpendicular to each other. Okay, and it's still moving with velocity v2, then start to slowly come down. Okay. So notice your v1x there is being done here. Draw again down here. So here your v0x, okay, this particle is component in the, or the velocity in the x direction. When it reaches this position, you look at the length of the arrow, represents, it's a vector, represents your component of velocity in the x direction, same length. So v1x, which is reflected here, has the same length as v0x. It means same velocity component. Okay, your v2, which is same as v2x, same length as your v0x, as your v1x. So same. Your v3x, same length as your v0x. So the horizontal component, the x component of velocity remains unchanged because why? The acceleration in the x direction is 0. Only the vertical direction of vertical velocity, the value will change because it is subject to a constant gravitational acceleration. So velocity will change. Okay, all right. So like you can see, you can put it in this way, like the shadow, shadow of the particle moving the projectile. Right? It goes up, or you can look at the side. You look at the side, okay, of the trajectory. You see, go up like that, and it come down. All right. So these are the important points you need to know. The x component of velocity, no change. Only the y component of velocity will change. Okay, and ay is equal to minus g. And you can use equations of motion. Okay, and note, initial angle is alpha naught. As the projectile goes up, it's no more alpha naught. It changed to alpha. Different angle already. Okay, different angle. Alpha naught to alpha, alpha to alpha 1 and alpha up, further up alpha 2, further up alpha 3, and so on and so forth. Eventually, alpha will 0 at the top. Alpha is 0 at the top, where the velocity of projectile v2 is perpendicular in direction to the vertical acceleration. Okay, so you can use your equation of motion to find your alpha, because your alpha is contained, will be contained later on, it will be contained in your, okay, there. V naught x is what? Is equal to V naught cosine, I written it for you already previously, alpha naught. So you can, alpha naught will be in your solution. So if you have to find alpha naught, then you can find alpha naught from here lah. Okay, and then V naught y, remember, is what? V naught sine alpha, V naught sine alpha naught. Okay, all right. So, all right, 12 o'clock already, very fast. Okay, so these are the summary. Okay, that's where alpha naught is, this summary. Okay, all right. Now, what if you want to find the distance r from the origin using Pythagoras theorem? This Pythagoras, okay? Pythagoras, okay? And find the magnitude of the velocity, or find the distance r from the origin, even direction of the velocity in terms of alpha naught. So what are all these? Okay, let me see, it's shown here. It's shown here. Let me look at that again. So if you, let's say, want to find r, so that's your r, see? Vertical. So that is your r. Okay, let's go back here. All right. So that will be your x, that will be your y, is 90 degrees. So Pythagoras theorem, distance of the particle r from the origin is square root of x squared plus y squared. Pythagoras theorem. Okay, that's your r. See that? Then same for velocity. Velocity, I've shown here also. How to find a velocity? Is square root of v1 x squared plus v1 y squared. Pythagoras theorem, to find your resultant velocity v1 here. Okay, so that is, you've got this one now, you got this one, vx squared plus vy squared. Anywhere along the trajectory, you see, is simply v1 x squared plus v1 y squared. You'll get your v1 here. And same for the next v2, same thing. Okay, and so on and so forth, using Pythagoras. Then the angle is simply is trigonometry lah. Okay, tangent alpha naught is v naught y over v naught x, and at any point becomes alpha, is vy over vx. Okay, so you see, tangent alpha naught is goes v naught y, okay, over v naught x, v naught y over v naught x. At anywhere here, tangent alpha will be v1y over v1x. Okay, v1y over v1x. That's why it's reflected here. Oh, okay, and it's alpha. So at the next point, next one, let's say tangent alpha 5. Tangent alpha 5. Alpha 5 will be vy 5 over vx 5. Okay, then you can find your alpha. All right, so it's simply Pythagoras theorem and trigonometry. Okay, Pythagoras theorem and trigonometry. All right, let me see. Okay, so the equation of the trajectory, that means the curve, is given at this one. Just take it because the derivation, I don't need to worry about the derivation. Take this as a formula. So what is this equation? This is the equation of the curve. Okay, equation of the curve. There, equation of this curve here, parabolic. That's all it means. So this is your alpha naught. There's your x, and that is your y. Okay, and that is your v naught, v naught. Okay, all right. So that's the equation of this trajectory. Okay, that means it's y position. It's given by what the values of all these, and you find what is this y position. Okay, for example, here, for example, that's your x. Where's the y? Here, y will be this value. Okay, so there'll be your y, is your x. Cool. So by apply this formula, you can find your y, or you're given a y, you can find its x position. or given y and given x, and given v naught square, you can find alpha naught, and so on and so forth. Okay? All right. The final 2 slides of relative velocity. Very straightforward. If you watch an air show, you see the airplane all flying above you. Okay. Now, as far as the airplanes are concerned, to each of the pilot, relative to each other, because they're flying in formation, you see. So you're behind, if you are directly behind the plane in front, okay. So your relative velocity would be 0, you see, because it appears that the plane in front is not moving at all, because you're always at the same distance from him. Okay, but as the observer on the ground, the plane is flying past above you, so the velocity that is apparent that you see is different. Okay, so the plane will fly past you and you watch them. Their velocity to you is a relative velocity. Okay, as it zoom past overhead, they are traveling at a different velocity from the to you and that's your relative velocity. Okay. Another example, you have a train that is moving along the x-axis. Okay, train B, a passenger walking along the aisle of the plane, and then you are cyclists. Okay, so if the passenger is moving relative to the cyclist, we denote the velocity of passenger relative to the cyclist as Vp/A. Velocity of passenger relative to cyclist. Okay, that's how we denote it. Passenger moving relative to the train, to train, and train is moving relative to cyclist. Then the x velocity of passenger relative to cyclist is denoted as this, you see. Velocity of passenger, train passenger, relative to cyclist in the x direction. And is given as velocity of passenger relative to train in the x direction plus velocity of train relative to cyclist in the x direction. Okay, this is actually a vector form, in vector form. Okay, this just very briefly. All right, any questions up to here before we take a 5-minute break? Okay, we'll take a 5-minute break. I'll check your chat box, then we'll come back. Okay, take 5. Take 5. See you later. Okay, let's resume our lesson. Judging from the time that we have, remaining time that we have now and the lecture materials, we won't be able to finish today's lesson, the materials, by 1 o'clock. I would like to propose that we extend today's lesson by half an hour. Is that okay with you all? Is that okay? So that we can finish today's material. Okay, Noah is very good. Noah said, no problem. Good. Naya also. Okay, good. You are very interested, very enthusiastic students of physics. I'm very, very thankful for you. Okay, so we extend today's lesson by half an hour. Okay, so we can finish. And so a certain part of the slide, I may have to go a little bit faster because they are very, very basic knowledge. So I have to go a bit faster. I'll spend a bit more time for a bit more complicated concept. Okay, all right, very good. I'm very thankful. We extend, but of course we'll have another 5 minutes break later on because it's until 1:30. Since we are extending it by half an hour. Okay, very good, very good. Recording, yes. Yeah, dental appointment, then of course you can go for a dental appointment. That'll be recorded. I think this is recorded, isn't it? Can you all check that it's recorded? Let me see. I think I don't see any, but I think it should be recorded. Oh, it's recorded. Okay, that'll be good. Yeah, okay. All right. So we are now into the last part on Newton's laws of motion. Okay, we are in dynamics already. So we will be, the end outcome will be all this. Okay, to understand more about forces, and forces, as you know, are vectors. And to know what is net force. What is net force? And that force, a net force will cause acceleration. Okay, and all right. And we know what is a mass, what is weight. So I'll move through mass and weight very fast. And how to analyze the effect of forces on two objects on each other and how they're related. Then we learn how to draw free body diagrams. That's very important. To solve a physics problem or any technical problem involving mechanics of bodies and objects, you need to draw the free body diagram correctly. Because if you don't draw it correctly, you will not get the right answer. And then we look at frictional forces, and how to solve. Very important. So these are all we cover, as I just mentioned, because those are the outcomes, and this is what we will cover today. Okay, including the free body diagram, frictional forces. Okay, we also learn how to superposition of forces. Mean how to combine two forces to get the resultant force. And then in the opposite direction, how to decompose a force into its components. Okay? To split one force into its x component and y component. Just like the projectile, we have the x velocity component and the y velocity component. So decomposing a force into its components means decompose or resolve a force into its x component and y component. Superposition, that means you combine two forces to get their resultant. Okay, so it's opposite to decomposing. All right, force we know, you push or you pull, you get a force. So normally you pull, you require a cable to pull. Push, very simple. Okay, so force has magnitude and direction. Now we talk about contact force. So contact force normally denoted as Fn. This in contact with what? Contact with the surface. Your tabletop on the ground, table, for example. So there will be a contact force. And this contact force is specially given a name called normal force. So it's presented as Fn, or here as N, okay, or capital N. All the same, like AKA, also known as N, also known as N capital. Same thing. It's contact with the table. See, normal force is also referred as normal reaction. Same thing. Normal force or normal reaction. Same thing. It's Newton's third law, you see. Because the object is sitting on the floor, on a table. So it's exerting a force on the table. And that force is the weight of the object on the table. So according to Newton's third law, okay, action and reaction are equal and opposite. So that the body, let's say you feel that there's a force pushing on you up in accordance to Newton's third law, and that force is called Fn, or normal reaction. This is in accordance with Newton's third law. Because mg acting downward, so Fn will act upward. Fn is equal to mg, equal and opposite. Remember Newton's third law. Okay, so a contact force is always a contact force. So this is still Fn. Even if your table is tilted, Fn is still Fn. So it's perpendicular to what? Perpendicular to the contact surface. So Fn is not always vertical, depending on the contact. If the table is tilted, Fn must always be perpendicular to the contact surface. Okay, right. So now another contact force is the frictional force. So if you were to move an object to the right, it's shown here, okay, to the right, and if the floor is rough floor, then the object will experience a frictional force in the opposite direction to the motion. Okay, in opposite direction to. So frictional force will always oppose motion or prevent motion. Okay, so frictional force sometimes denote as FF or simply F. Right, different ways of denoting the same thing as long as you define what it is. Okay, right. So direction of frictional force is opposite to direction of motion. So frictional force. So when you draw a diagram like that, you may say, I want to have such a big box, a big block here. Can I make it to a small dot? Also can. Okay, same. Can make it into a small dot. So a frictional force will be opposed motion. Okay, motion. It's a motion. Always oppose motion. And a normal force is still normal force. Must be perpendicular to the contact surface. So this is rough floor. Rough floor will produce friction. Okay, let's move on. Now another type of contact force is a tension force. Tension force is basically exists along a rope or a cable. rope or cable or string or wire or whatever, you actually pull it and you call the force along the cable as tension force T. That's all. Tension force. It's a force. Okay? All right. So force is a vector. It's magnitude. That you all know. So how do you measure the force? Yeah, you put a spring balance there and tie it to a cable, the red arrow cable, and you pull it. Okay, then you see what's the force you apply. It is shown on the scale of the spring balance. Okay, right. Okay, several forces can be combined. Okay, for example, you have F1 acting on this box or this mesh, F2. So you have two cables. One is F1, one is F2. So F1 can be called tension, tension T1, F2 can be T2. But we can sometimes refer to the tension as force. Okay, because tension is a force anyway. So these two forces combine to pull the box is equivalent, will give a resultant R in the direction of the arrow. Okay, so this is superposition of forces. So F1 and F2 will result in the resultant force R in that direction. Now, on the other hand, if you use just one string or one cable, you pull the box, along a incline. Okay, along an incline. And when you encounter an incline, one of the things you must do wisely to make your life easier is to rotate your X and Y axis so that your X axis is parallel to your incline. Okay, your X axis is parallel to your incline, and the Y axis is perpendicular to your X axis, of course, to make your life easier. So when you have put a string there tied to a box and you pull it, try to pull it up the incline in this way at a certain angle, theta. Oh, wait. Oh, I didn't know that was theta. So let's change it to alpha. They're not the same angle. So alpha, okay? Because the other one is theta. So you pull it at an angle theta from the positive x-axis, okay? So this force along the string or the tension can be represented by its two components. One along the x-axis, the other one along the y-axis. Okay, the one along the f-axis is called fx, and by now you should know fx is equal to what? F cosine theta, and fy is equal to f sine theta. Okay, so when you have fx equals f cosine theta and fy is equal to f sine theta, you can then forget about f already. Okay, you can then forget about f in your solution. Don't put f, still have in your solution. Then you have additional force already. So in your solution, you only deal with fx and fy. No more f. Okay, so we cross out the f once you got fx and fy in your, okay, and you use them in your solution. So fx and fy are components of a force along the x and y axis. Okay, then you can go and solve. Okay, so there's two forces. So in this case, how would you solve? Okay, there's another example here. You have a hook, a ring hook like that. You screw it in there, then you tie two strings, and you pull the hook. So one string will have F1 or tension F or T1, what we call it F1. Another string will have F2. Okay, so therefore there will be a resultant force. By now we should know there'll be a resultant force somewhere along this direction. This is your R. Okay, so the ring will experience a force, a resultant force, pulling it in this direction with this magnitude R. Okay, so now remember this is schematic, help you to visualize the problem. But when you solve the problem, you must use the vector diagram to solve, or else you will not get correct answer. Okay, so the vector diagram is that first you got to resolve F1 into its X and Y component. So your F1, you resolve it into your F1X component and F1Y component. Okay, then you can forget about F1 already. Next, you have your F2. Similarly, you must resolve F2 into its X component and its Y component. So F2, there, starting from here, you have its X here. So you have X component, F2X, okay? There, F2X, which is here, shown here. And F2Y, from there to F2Y, which is shown here on the Y-axis. We put it on the Y-axis because F2Y in the Y direction. This F2X in the X direction. So now once you have F1X, F2X, F1Y, F2Y, you can forget about F1Y, forget about F1 and F2 already. How do you find R? R is a summation of all the F along your X and Y axis. Okay, so which means that if you add F1X and F2X together, it gives you your resultant component in the X direction. When you add F2Y and F1Y together, you have resultant component in your Y direction, which means that you have your Rx, and your Ry. Now we are ready to find your R, you see. R will be there. Okay, so your R would be so your okay, this so define R from here. So remember, you need to transfer your Ry to here. Okay, so I just want to let you know that's your Ry. But in your vector diagram, your vector triangle must close. Okay, there you are. So your vector triangle must close. All right. So how do you find R? Pythagoras theorem. All right. So R is equal to square root of Rx squared plus Ry squared. Answer ready. How do you find its angle? Whatever it is, theta. So tangent theta is equals to Ry over Rx. Answer, find theta. Because R is a force. It has magnitude given as square root of R squared plus Ry squared. It has direction given by theta. Theta will be arctangent Ry over Rx. So that will be your answers. Is that clear? When you want to have two forces acting on a component and you need to find the resultant force acting on this component and also the direction of this resultant force. Okay, right, good. Now, next on Newton's law. So Newton's first law there, every object remain at rest or in uniform motion means constant velocity, uniform motion or constant velocity in a straight line, remember, unless it's compelled. Compel means force to do something. Unless it's compelled, unless it's forced to change its state by the action of an external force. In other words, if a body is at rest, sitting on the table, okay, it will want to remain at rest. It want to maintain its status quo, means continue to remain at rest. It doesn't want to move unless you apply a force to move it. Then it will move. You have no choice but move. Okay? Or else it means it try to resist changes to its current state. Not just when it's at rest, but also not just at rest, also when it's moving at a constant velocity. Not just at rest, but also even if it's moving with a constant velocity, the object will still want to continue to move at this constant velocity unless a force is applied in the opposite direction to stop it, or to move it faster in the other direction, to push it more so that you move faster, or to stop it, you have resisting force in the opposite direction to stop it, or else the object will prefer to continue to move at a constant velocity. That's Newton's first law. Not just at rest, but also moving at constant velocity is also applicable. Okay. So when a body is at rest, we say that it is in equilibrium. Also, when the body is moving with a constant velocity, we say that it is in equilibrium. Okay. All must be in straight line. So in equilibrium doesn't mean only at rest, zero velocity. In equilibrium can also be is moving with velocity, but constant velocity. Okay, not accelerating or decelerating. At constant velocity. So for a body to be in equilibrium, it must be acted by no forces. Means no force must be acting on it. Then you remain status quo. Or by several forces. Then you're wondering, hey, a body acted on by several forces, how can it be at rest or still continue to move with constant velocity? Impossible, isn't it? Oh, yes. It's just about resultant force, right? Provided these several forces, their sum or their vector sum, means their resultant. The resultant is also called the net force. Okay, so just now you see R, that resultant. In this case here, it's also called the net force, and provided the net force is zero. Okay, so a body that is moving at constant velocity can also be acted by several forces, but the resultant or the net force on this body must be zero. Then it continue to move at constant velocity. Okay, the net force on a body, net force, this is the net force, summation F equal to zero. Net force must be zero if a body is to be in equilibrium. Meaning what? Either at rest or moving with constant velocity, or these two situations along a straight line, along a straight line. Okay, conditions important. Okay, now first law. Okay, so you have a hockey stick. This ice hockey, ice hockey. Okay, hockey stick. All right. So if the hockey stick apply a force F1 on the disc, okay, that means there's a net force F1. No other force involved. So that is the only force, and so that's the net force F1. Okay, ice surface, frictionless, ice surface, frictionless. It will accelerate. So the hockey disc will start to slide along the ice. Okay, with an acceleration, acceleration. So we're done off now with net force equal to zero just now. Net force is zero. Now net force not equal to zero. We have a net force now is not equal to zero. We are moving into Newton's second law already. Previously, first law. Now going to second law. So first law and second law are actually related. Okay. All right. Now we're going to second law. So it will accelerate. So here, summation of force is zero means no acceleration. It's the equilibrium. It's still moving at constant velocity, or it is at rest. First law. Okay. Still moving at constant velocity, no acceleration. Now it's going to accelerate. We're going to second law because net force not equal to zero. Summation of F not equal to zero. Second law. So previously, first law, when a net force zero, acceleration is zero. Okay, because it means constant velocity. It's still moving with constant velocity or stationary the net force is zero. So this is in equilibrium. So like that, if you have a disc, ice hockey disc, and you have force acting this way and one force to the left, one for the right, clamping it like that. And if F1 equal to F2, okay, F1 must equal to F2 if there's no acceleration and the net force is zero. It's clamping it. So we say the net force, summation F, is equal to zero, is equal to F1 plus minus F2, because F2 is in the negative x direction. So therefore, 0 is equal to F1 minus F2, and F1 equal to F2. So this is a case of net force equal to 0, where Newton's first law applied. Okay, so we are moving back and forth. Okay, first law, then second law, then back to first law. Okay, so now you have a cable again, and you pull with acceleration. You pull this mass. So you have a net force equal to F1. That's your F1. Okay. So you move with acceleration A. Okay. Now, if you double the net force, if you double the net force, you double the acceleration. You halve the net force, you halve the acceleration, which is easy to understand. Okay. So so the acceleration alpha or LA is proportional to the force. Double the force, double the acceleration, triple the force, triple the acceleration. So we therefore say that acceleration is equals to something times force. There's a constant of proportionality. The constant of proportion is your m, mass. Mass. Therefore, you can say mass is equals to F over A over acceleration. Okay, mass in kilogram. But this will all lead us to second law. Second law. Okay, so all right. The larger the force, the greater the acceleration. And this leads us to second law, Newton's second law. The acceleration of the object is directly proportional to the net force and inversely proportional to the mass. Okay, it's directly proportional to the net force, inversely proportional to the mass. Okay, directly proportional to the net force acting on it, and inversely proportional to the mass. So this is leads us to Newton's second law. F equals ma. So in this case, ma is not equal to 0. 0 is actually first of all, first law is applicable. First law and second law are very related. Actually, all the Newton's three laws are all related to one another. Okay, so this is now second law, where there's acceleration. So your net force summation F not 0. Where is mg? We all know. Okay, so that's for horizontal. Just now horizontal x motion. What is vertical motion? Falling body, vertical motion. Okay, it's falling. This body, its weight is mg. So subject to a force mg, moving it down. So its acceleration is g lah. Is g. Okay. So the net force that's causing the vertical straight line motion is equals to mg. Okay, mg. But if it's hanging from a string, hanging from a string, then it's stationary. Okay, that's hanging from a string, it's hanging a string there. Then of course it's stationary lah. No acceleration, no velocity. So net force is 0. But it's falling. Net force is the weight, the weight that causes it to go down because of gravitational acceleration. Okay, then you have the case of astronaut in space. As you know, on Earth, we are subject to gravitational acceleration g. But in space, the gravitational acceleration gets less and less, eventually to 0. Okay, so and even on Earth, you can experience apparent weight. Means not your actual weight. Apparent means appear to not actual weight. So if you are a passenger on a lift, and your mass is m, you ride in the elevator, a lift. Elevator is American, British is lift, and the lift is accelerating upward, ay. You step on a scale, a scale balance, a balance scale, a weighing balance scale. You step on a scale inside a lift. The scale will show your apparent weight as whatever value it is, your weight, apparent weight, and that is given by your mass times bracket g plus ay. G is standard. Mass is your mass, cannot change. It's the ay that will vary. Because ay is positive upward, the lift is going up. And you're standing on a weighing scale inside the lift. And the scale will give you a reading equivalent to n, not your actual weight. So will your actual weight increase or decrease in this case if your lift is accelerating upward? Increase or decrease? Your weight, your apparent weight will be higher than actual weight or lower than actual weight. Very good. Lee Kim Liang, Liao Hong Guan, Dawson, very good. It will increase. Okay? It will appear to weigh more because the lift is pushing you up. So means you're pressing more on the scale because the lift is going up. So you are pressing more on the scale. So you appear to be heavier. Okay? All right. So this is a formula to use. This is a formula to use. If any question on person inside the lift and the lift is accelerating up, and that is your there. AY is positive. But if the lift is accelerating downward or free fall, let's say unfortunately the cable snap. The cable snap, poor fella. inside the leaf will experience a free fall, and your acceleration in the y direction will be minus g, okay? Because the leaf is going down, accelerating down, free fall. Free fall means you're subject to a constant gravitational acceleration of g. And because it's downward, therefore, your ay is minus g, okay? So in this case here, when ay is minus g, when you apply it to your above formula in the box, it goes to mg plus minus g. So n become 0. You will experience weightlessness. You will experience weightlessness. So many millionaires, they're spending like the $1 million to go up to space to experience 45 seconds of free fall, weightlessness, They take a special space vehicle like SpaceX, Elon Musk, and some millionaires spend $1 or $2 million for the trip and go up to outer space, and then outer space, the vehicle will free fall, and then the passenger never experience about 45 seconds of weightlessness before the engine comes back again. Okay, but in the leaf, this free fall is the last moment on Earth. The last the leaf free fall. Oh, that is terrible. Okay, because it experience weightlessness and because the leaf is free falling. Okay, so similarly as an astronaut in space, outer space will experience weightlessness. Okay, so remember that formula. Ay positive upward. If it's downward, Ay is negative. If the leaf is accelerating at, let's say, the 3 meter per second, okay, then the Ay is minus 3. 3 meter per second squared. Okay, all right. Next, third law now. We're going to go third law. Action and reaction are equal and opposite. Basically, when two bodies interact, the two forces that they exert on each other are equal and opposite in direction. Okay, action, and you kick the ball with a force is your foot apply a force of Fa on the ball B, A on B, foot on ball. At the same time, you experience a ball exerting of equal and opposite force on you. Force of ball on your foot. Okay, this is Newton's third law. So Fa on B is equals to minus Fb on A lah. Equal and opposite. That's your minus sign. Opposite. Okay, right. Okay, next a free body diagram. Free body diagram. Okay, is to identify all the relevant forces on a body. And this is a guide. What you should do, how do you do it. Draw a vector diagram. Does not include forces on body exerted by the surrounding. Must be include all the forces and do not include force exerted on any other body, and so on and so forth. Okay, I need one body at a time. If you have two bodies, then separate diagrams for each body. Okay, so this is for you to yourself study. So now in this case here, it's good to learn how to draw free body diagram. Many physics problem or mechanics problem start with free body diagram. So in this case, draw a free body diagram for each of the following as specified. Okay, so now, okay, so maybe what I do is to refer to the visualizer to draw, because there's quite a number of diagrams here. Okay, advance. Okay, yeah. All right, free body diagram. Look at the. Okay, let me give you the example. Example, simple one first. If you have a little, let's say a little a river, a shallow river, okay, and you put a plank. There's a plank. Okay, and you stand on it. You stand here. Okay, and these are points A, contact area, B, contact. This middle, C, C middle. Okay, that's the water, C. Draw FBD. Draw free body diagram of plank. Okay, the simple example. So how do you draw a free body diagram? So this is schematic. Now we're going to draw FBD. You will draw a beam. Because a prank, this is a prank. This is a prank. Okay, draw a line will do. You want to draw a thick line or a box also can. So you have your points A and B.
So this is A, this is B, middle is C. So it means you must draw all the forces acting on the prank, because the prank is the body. The prank is the body. So first, the prank has weight. So weight prank. M of the prank times G. Okay. Then you have weight. You also add on the prank. So you have weight. So so your weight here. So you there. Mass of student on the plank. Mass of plank acting on itself. Mass of you student on the plank center. Then these are contact point. Contact point, remember, the plank is pressing on the ground. So according to Newton's third law, the plank, you or the body, will experience a equal and opposite force acting on it. So this equal and opposite force is called reaction. Reaction at A on the plank. The plank is the body. Likewise, B will experience a reaction B by the ground on point B. Okay. So after doing that, you also need to put the dimensions. For say from let's say, all right, I mean, is there to here, for example, is 10 meter. All right. So this will be to the boy there is 5 meter. So you got to put there the length 5 meter, this whole length 10 meter. Standing at the center. So there's a FBD of the body, which is the plank. Okay, all the forces are there. Don't miss any force. If you miss any force, you end up with wrong answer. Your calculation solution will be wrong. Also include the distances also. If there's an angle, must also put in the angle. If there's angle, in this case, no angle because horizontal plank. Okay, so now we'll answer the question on the slide. We'll answer the question on the slide. 1, 2, 3, 4, 5, 6. 6. Okay, 6 free body diagram we need to sketch. Okay, so are you ready? Let's sketch them. So now we know free body diagram. Okay, now, okay, first one, ceiling. The ceiling, the object hanging from the ceiling. How is the free body diagram like? So the free body, you need not draw a big box. You can also draw a small box, or even a dot also can if you like. Okay, this is the mass of the object. So the mass, this box, will have its own weight, of course, acting on it, mg. Now it has got 2 ropes, so there'll be 2 tension. Okay, so you can put that one. Okay, you can put there. Okay, FT and FT lah. FT and FT. All right. Or you can put like little dot here, mg, and here 2FT. Also can, because all these forces are captured. Okay, and you assume that the 2FT are very close to each other. Okay, FBD of object. So it's FT or T, or T. It's 1 p.m. Okay. Okay, we'll finish this, then we take a short break. Okay. All right. FBD. Number 2, you have the boy sliding down the slide. Okay. The boy sliding down the slide. So that is the free body diagram of the slide. FBD. This FBD of mass. Okay. Next one, FBD of the FBD of the, yeah. Okay. Okay, so you have your slide here. FBD of the boy, the boy. So this is your slide. Now this is a boy. Okay, so we know that the boy has got weight, so his mg, his weight. All right. Now he's sliding down. It's a rough surface. Okay, rough surface. Rough surface. So there's a contact force called a normal reaction. Normal reaction always perpendicular to the contact surface. Okay, 90 degree. And what else? There is frictional force, opposing motion. FF, friction. So FBD of boy. Okay. All right. Now, if you are asked to draw, also include the components. Notice that in this case here, this is your x-axis, this is your y-axis. You must rotate. So you have component of your, because FF is along x-axis, that's fine. Fn is y-axis, that's fine. But mg is neither parallel to x or y-axis. So what you do is, when you do your calculation, you must resolve your mg into its y component and x component. So its y component is mg cosine theta if this is theta. Okay, then your x component is mg sine theta. So once you have mg cosine theta and mg sine theta, you can forget about mg in your solution. Then you continue your solution to get your whatever answer you have to get. 3, it is man pushing a cupboard on a rough ground. Okay, so we can represent cupboard with a box. Okay, so there is pulling it. All right, so you have T or F also can. Cupboard, mg, weight, normal reaction, and what else? Frictional force, FF. Okay, FBD of cupboard, whatever. 4, you have a mother putting a daughter on a sledge on the snow ground. Snow ground. Snow. And the snow also has some friction, you know, because snow is not ice. Snow has some friction. So how's the FBD like? For the little girl on the sledge. So girl and sledge together. Their total weight, okay, mg, total weight, girl and sledge. So your mg, you have your normal force. Okay, you have the tension in the cable, your F tension, if you like. Then you have friction, FF. Okay, so it's snow, so it's rough, rough ground, not ice. Snow has friction. That's your FBD. Okay, so FBD of girl and sled. Okay. So far, so good, All right, next, you have two masses. They are in contact with each other. Two masses in contact with each other. Okay, so how's your FBD like? So remember, two masses interact. It's a free body diagram, one body at a time, not free bodies diagram. So one body at a time. When I draw free body diagram. So you have your first mass, M1. Okay, your M1. You have a force applied, which is there. That's your given. Okay. So it's sitting on the rough ground. So rough ground. So, well, first thing you got to do is, of course, mg. M1g. Then you have your normal reaction, Fn1. Okay. The force trying to push it in this direction. So there'll be a frictional force that will oppose, FF. Okay. Now, because these two masses in contact, so there'll be also be a force of 1 on 2. Okay, force of 1 on 2. There will be a reaction force because this will press onto the M2. M2 will push back with equal and opposite reaction. This from M2. Now, you go to M2. Same, you have your M2G. Okay, then you have your frictional force as usual, FF2, FF1, FF2. Okay, then you have your Fn2, normal force. You have your force due to its contact with M1. These two are equal and opposite. This due to F1, the force due to F1 pushing on the mass M1 is acting on M2. So Newton's law, you have a force applied to it on here due to contact between M1 and M2. So M2 will produce an equal and opposite force on M1. So these two are equal. Okay, rough surface, 5. All right, 6, pushing the fridge, all right. Rough floor, as usual, mg. The man is pushing it, have applied force, Fa, man pushing. Normal reaction, Fn, and frictional force, Ff. Okay, so all these forces Must be there lah. Then you can do your calculation. Is that clear? All right. Okay, all clear, huh? You want to have a 1 minute bio break? You want to have a 1 minute bio break? Okay, let's have 1 minute bio break. Then we come back, okay? 1 minute, huh? See you 1 minute's time. Okay. Yes, yep.
What's the difference between inertial mass and mass of object? Like, is there a difference? Or?
Inertial mass and mass, normally we don't call inertial mass. We call it moment of inertia, which is different from mass. Mass is standard mass. For example, object's mass is 5 kilogram. That's very standard, you know. And its weight, the object's weight is 5 times g, Newton. So inertial mass, basically, I think it only adds to confuse students. Mass is mass lah. Inertia, basically, by definition, inertia is the tendency to resist change. Inertia means tendency to resist change. So we seldom talk about inertial mass, although you may on some internet you may come across inertial mass. There's some fanciful name. A mass is a mass lah. Okay, and a mass, of course, has got inertia lah, because the mass itself it won't move on its own. It want to continue to remain at rest if it's resting. So it has inertia in that sense. The tendency to resist change. To change means to move it. You have to apply a force to move, then the mass will move, or else the mass don't want to move because it has inertia. So some people want to call it inertial mass, make it sound very high technical. Actually, mass is a mass. And mass is itself has a tendency to resist change. Okay, but we don't usually call it inertial mass unless you want to sound very, very complicated. Mass is a mass, but inertia, we have moment of inertia, which is totally different from mass. Okay, all right. All right.
In one of the slides, they use the word inertial mass.
Okay.
Is that different?
Okay, but it doesn't matter. Inertia, because mass itself has inertia.
Yeah.
Okay, so inertial mass. Then we say, sometimes we say but basically it's mass lah. Okay, not to worry. Inertial mass is the same, but bear in mind that moment of inertia is different from mass, or so-called inertial mass. Okay, all right. Okay, all right. Okay, and now 30 seconds left, and then we'll come back. Okay, all right. Let's come back after the short break. Yeah, okay. Next, we did mention about frictional forces in our earlier slides and even the free body diagram. Okay, so friction. Now, the first question I want to ask is friction dependent on the surface area of contact? Is friction dependent on the contact surface area? What do you think? No. Okay, good. Your memory is good, because I did mention that frictional force does not depend on the surface area. It depends on the materials of contact and also the contact surface condition. Okay, that's very good. All right. So friction resists motion. Okay, resists motion. Okay. All right. So, okay, frictional force, basically, if you apply a force, okay, frictional force always oppose motion. Okay, oppose motion. And when you actually drag a body across a rough floor, okay, the contact force, because when it's not, okay, oops, sorry. Now, when a body is stationary on the rough floor, okay, there's your mg, there's your Fn, stationary. All right. Now, when you drag it along a floor, okay, with F, F apply. Where is this? So this is actually a contact force on the rough floor. The contact force is no more vertical already. It's actually somewhere like that. The contact force is actually like that. And it's no more called Fn because no more normal to the contact surface. No more called Fn because Fn means perpendicular to the contact surface or normal to the contact surface. When you drag it on the rough floor and it's moving in this direction, then the arrow goes slanted really when you move on a rough surface. Okay? So the diagram on the left, you have your normal. It would resolve this contact force into its vertical and horizontal component, you'll get your this one and your frictional force. So the normal force component N and the frictional force component F, these are actually your Y and X component forces of your contact force. So now you got normal force N and frictional force drawn on your FBD. You can then forget about your this force. Okay. So in other words, when it start moving, it becomes okay. When it starts moving already, this should be your applied force. This should be your frictional force. Okay, this is your mg. This is your fn. Okay, that's your FBD. When it's moving, or even when it's not moving, even when it's not moving. That means when it's not moving, it's an impending motion. This also applies. When a body rests or slides on a surface, this would be the FBD, you see. This is the, sorry, this is the FBD, okay? This is the FBD, where is it now? Okay, so this is the FBD, this one. Whether it's sliding or resting, this is the FBD on a rough surface. Okay, now we want to talk about kinetic frictional force, FK. This FK occurs when the body slides over surface. So FK is mu K times N. What is mu K? Coefficient of kinetic friction. Okay, N is normal as usual, your Fn. Okay, kinetic means when the body is moving, when body is already sliding, okay, not stationary, no, it's sliding. You use this formula. Fk is equals mu K times normal force. But when the body is not sliding, okay, no relative motion, okay, you apply Fs, static, okay, where mu s is a constant. It's called coefficient of static friction. Coefficient of static friction. Meaning, when you have a body, you apply a force, Fa, okay, on a rough surface, okay, and of course you have your mg, you have your Fn, then of course you will have frictional force Ff. Now, stationary means at impending motion, okay, what I'm saying is that before impending motion. Now, when the Fa is small, applied force is small, you find the body doesn't move. Why you apply a small force? You apply a force, why the body doesn't move? Because there's frictional force that will equal to Fa, equal and opposite. Now you increase the force a little more, you find that this block also doesn't move. Why? Because the frictional force also proportionally increase to equal Fa. Now increase Fa now to even more, then you find the box still hasn't moved. Why? Because the frictional force also increase proportionally to equal that of Fa. Okay, that's why the box doesn't move. So you see that the frictional force actually grows or increases proportionally with your applied force. And now, if you increase the applied force just a little bit more, you find that the box is about to move already. It's moving, then stop. You can see that it's jerking. It's about to move. This is the point of impending motion. It's just about to move. Just about to move. Okay? Just about to move. Then your F static friction force is equal to mu S times your normal reaction. Equal. Now you look at the left formula, is less or equal. Means when the Fa is very small, frictional force is less than mu S times your normal reaction, even though it's still growing with Fa. So when you increase the frictional force also grows a little bit more. And now you will see that you increase Fa a little bit more, the body starts to want to move already. Then this is impending movement. It means frictional force now grows to be equal now to your mu S times N. Okay? So at impending motion, you use equal sign. And this is normally the frictional formula that we use. static frictional force, in other words, frictional force at impending motion is equal to mu s times n. Okay, this is a friction formula. Now, once the body starts to move already, it's moving at a constant velocity. So now the body is moving at a constant velocity already. You don't use mu static anymore because no more static. You use mu k, kinetic means movement or dynamic. Kinetic means dynamic. You use Fk is equal to mu k, no more mu s. Mu k times the same normal force. Okay, so when it starts to move already, you don't use Fs is equals to mu Sn. Mu Sn. You use Fk is moving already at constant velocity. So use Fk, frictional force. Fk is equals to mu k, kinetic coefficient of friction times the same normal force. And because the mu k is generally smaller than mu s, so your Fk is generally smaller than Fs. Because mu k is generally less than mu s, so your Fk is generally less than mu s. Your n is the same, no change. Okay? So mu k is a coefficient of kinetic friction. Mu s is coefficient of static friction. That means at impending motion, at just about to move. Use Fk and mu k only when the body is moving already, sliding at constant velocity. Okay, right. Okay, this we know. If it's not moving, frictional force 0. Once you start to move, okay, frictional force, and when it haven't moved yet, it's still stationary, it's less. Frictional force less than mu Sn. But increase T or increase the applied force, Fs will continue to grow until equal. Okay, until equal to mu Sn. Then it is at impending motion. Object is just about to move under the applied force. Okay, all right. Now, once it started moving already, you use Fk and mu k. It's already moving. Okay, n is the same, no change. Okay, it's already moving. Object is already moving. Moving at constant velocity. Moving already, Okay, right. So this plot shows frictional force with the applied force T. So this is a plot. So in other words, you have a body, when the applied force is 0, frictional force 0. Okay, on a rough surface. When you increase the applied force to T1, see the frictional force grows to F1. Go to F1. When you increase the applied force to F2, to T2, frictional force also grow to F2. That's why object remains unchanged, still stationary, never move. Now, when you increase it to T3, what happened? Frictional force grows to F3. F3. This is your F3. Okay. Not to worry. Sorry. T3, F3, wrong. F3 is wrong. Wrong point on the. It goes to F3. F3 is here. This is your F3. Okay. So T3, F3. So F3 is the maximum that your frictional force can grow to. It cannot grow any further. So once you increase your T by a little bit beyond F3, just a little bit, just a little bit only, what happened? The box will move. So this is the point of impending motion. It is just about to move. Now, once you increase T3 to just a little bit to the right, what happened? It moved. When it moved, what happened? You no more use Fs already. Here, your frictional force, your Fs, F3, which is your maximum, your Fs maximum, is equal to mu s times your normal n. Okay. So once you move, increase F3 to a little bit to the right, what happened? It starts to move already. And when it moves already, the frictional force is no more F static, it's Fk. Fk. And Fk is always less than your F max, Fs max, as mentioned earlier. Okay. As the mass continue to move under the action of the T towards the positive X direction. So this will be your kinetic frictional force. And why is it goes zigzag? Because the rough surface, so sometimes a bit more, sometimes less. So you stick on, then become non-stick, stick then loosen, stick as you drag the body across the rough floor. So nevertheless, you can say it's a straight line. Okay, a straight line. So your kinetic frictional force is always less than your static frictional force. And your Fk is equals to mu k times your n. Okay, always less than your Fs max. Okay, all clear? And this is your last, I think, last slide. So this gives an idea of the various mu s and the various mu k for different materials. Okay, so we see that in general, mu s, in general, mu s is greater than mu k in general. Okay, look at the values there. Okay. Right, so I'm finishing summary. Force is a vector, has magnitude and direction. Newton's first law, summation of forces in the positive x direction is 0, means net force. This is net force equals 0. If the body remains in equilibrium, that means remaining at rest or is moving at constant velocity. Okay. Newton's second law, that means net force not equal to 0. There is a net force not equal to 0. And because it's net force not equal to 0, so there is acceleration. So net force equals the mass times acceleration. Weight is mg. Okay. Newton's third law is action and reaction are equal and opposite. A on B is equal to B on A. Okay, straightforward. Kinetic friction, Fk, is equal to mu k times normal reaction. Static friction, Fs, use this formula back. Is Fs is equals mu s times normal reaction. Okay. At impending motion, about to move. This one already moving, already sliding. Then you apply. Okay. All right. Come to the end. It's about 1:30. Any question? I finished all my materials already. Thank you for your patience. I really appreciate very much. Let me check your box whether you have any question or not. No question. Wow. Okay. Very good. Very good. Very good. Okay. Anyway, as I mentioned, if you have any questions outside my from now on, you can always email me. Okay. You can always email me. All right. Okay. So thank you for your patience today, and all the best to you all. Thank you. Bye bye.
Right. Thank you, Prof.
Bye.